Right, we're into chapter 2, and so here we want to look at the definition of a limit. And we're not going to hit this really hard, but I do think it's good to see this. If you had me for Calculus 1, you saw this. Um, I don't know if you didn't have me for Calculus 1, whether you saw this or not. Um, but it's good to see this a little bit, although we aren't gonna push it real hard. Um, now the big thing here is, they say, well, suppose um, we've got f, which takes some subset uh, of the complex numbers um, to the complex numbers somewhere, and um, z0 is an accumulation point. Um, so let's look at that first. Just you only talk about a limit if for instance my set G were just a bunch of isolated points like that. If this were G, um, there's no need in talking about limit because you don't think of a process of say z values getting closer to something, um, and so then wondering if the f values do as well. Um, and so to get an accumulation point, so they wouldn't be isolated like this. Now the easiest thing would be, I've got a point z0 inside some, open set like this, and so z0 here is a definite accumulation point. I can get, I get closer and closer to it. But another possible accumulation point could be that you have points that are getting closer and closer together like that. Um, Now I drew these, I guess, from the other direction, so I could use a minus. But if I said something like minus 1 over n, as n heads out to infinity, right? These things are getting really, really close to 0. But each each one of them, each of these points is actually isolated, but the point 0 is an accumulation point. So, here in this case, z0 equals 0 would be an accumulation point for this set G. So you can have weird stuff. And I say weird just in that typically, I'm probably thinking of a set like this one over here on the left where, um, it's just some nice open set and nothing strange is going on. But when they talk about an accumulation point, you could have something more like this right hand side here. Um, so it can get quite complicated. We're gonna try not to make it so complicated. Um, we just want to look at let's make sure we get the definition and that we kind of remember some of this stuff about limit. And so our definition then is if uh, either W0 or omega 0, I think they're using a W, I guess, I think. W0 is an element of the complex numbers such that for every, and this is the important part, for every epsilon greater than 0. And so usually when we think of epsilon, we think of smaller and smaller numbers. We can find a delta greater than 0 such that, or so that, for all z in our subset G that we're taking this function from, with or satisfying satisfying that 0 is less than the absolute value of z minus z naught is less than delta. We have that the absolute value of f of z minus w naught is less than epsilon. Then w naught is the limit of f as z approaches z naught. And so we would write something like the limit as z goes to z naught of f of z is equal to w naught. Okay, so that definition, it's a game. Okay, that's the way I look at it. It's a game. Is if I claim the limit, in other words, you know, if I'm making the assertion that W0 is the limit, then you, my adversary, you pick epsilon and I produce delta. Okay, so that's the game, and so, you know, and they use this example. They do z squared to start with, but let's pick something maybe slightly easier just to start with. So suppose I want to claim that the limit as z goes to 1 plus I of 2z is equal to 2 plus 2I. Okay, as you look at that, it looks like, yes, it ought to be, right? Because if I plug in I plus 1 into 2z, I get 2 plus 2I. All right, so typically, although you know, you may not start this way, but often what you do is you simply start with the basic statement at hand up here of f of z minus w naught. And so we would take the absolute value of 2z, so there's f of z, minus 2 plus 2I, like that. Okay. And now what we need to get to, remember, is we need to get to something that looks like z minus 1 plus I, because that is what we need to make less than delta, right? So you're going to give me an epsilon, whatever that epsilon is, and I need to make this thing less than that epsilon by choosing this delta. Well, in this case, notice there's a 2 in every one of those terms, so this is equal to 2 times the absolute value of z minus 1 plus I. Okay. So, though, right, I need to make this less than delta. And so I'm going to say, oh, this is less than the 2 times the delta I pick. Okay. So, because I'm going to choose that less than the delta I pick. And so now, if this needs to be less than epsilon, then all I have to do is say, oh, okay, well, then I want that less than epsilon. So how would I have to pick delta? Well, choose delta less than epsilon over 2. Okay, and I just get that from playing that game right there. So, so that's the idea. Well, let's, I suppose we could now look at an actual epsilon just to see if this worked. So so sometimes I'll make this kind of epsilon, sometimes I'll do my epsilon like that. They're both epsilons. Okay, so let's just kind of look at this and see if that's the case. Let's choose, so suppose you gave me an epsilon equal to, let's make it kind of easy to work with. So say 0.2, and so what that means is I'm going to choose delta equal to 0.2 over 2 equal 0.1. And I'm going to insist that the absolute value of z minus 1 plus I is less than 0.1. But now, if I multiply through by 2, I will get that 2z minus 2 plus 2i is less than 0.2, which is what we insisted on, right? Is that by me insisting that this be less than 0.1, I was able to demonstrate that then we get our 2z minus w0 less than 0.2, the number you gave me. So you see, that's the game. And in this case, it was pretty straightforward to produce that epsilon. Well, actually the delta, sorry, given the epsilon, coming up with the epsilon over 2 was pretty straightforward. It is not always so straightforward. And, so we're not going to push this really hard, but I think, it's a good idea to kind of just see this game. And so that is our definition of a limit.